new topic we call the repeated squaring technique for polynomial evaluation. Here, this one is a smart method to calculate some special expression efficiently. So here, let me explain this method. Repeated squaring technique. From this, its name, you can see how do we, you know, the content of this method. Yeah. All right. Let me show you, yeah, a simple polynomial. Yeah. All right. So this is a simple polynomial. Yeah. All right. And when we do the evaluation, yeah. So here, let me just change the color of my pen. All right. Okay. So when we do the evaluation, we just learned Horner's rule, right? Yeah, Horner's rule. Here we know the Horner's rule is used for the general case. Yeah. So why it's the general case? Because here A0, A1, AN could be any numbers, right? Yeah. Very general. We do not require A0, A1 through N follow any special pattern. We do not require any pattern. You can apply Horner's rule. Okay? Yeah. All right. But when you have special case, when we have special case, so for the special case, Horner's rule may not be the fastest, because on the special case, we can do faster than Horner's rule. Here we consider the special case. Okay, all right. Here we consider, look at this. Yeah. Suppose I use P0 of x, this polynomial, equals x to the nth power. Is this special? Special, right? Yeah. Yeah. Monomial, only one term. One term, no coefficient, or coefficient is 1. Okay? Yeah. So it's a special case. That means you can use the special property in this case to get a better performance, better efficiency. Yeah. Think about if, for this special case, if you apply the Horner's rule, it's not very good, it's not the fastest way. If you apply Horner's rule, because Horner's rule tells us the number of multiplications equals the degree number m. Here, if you use n multiplications, not very fast. Not the fastest way. Not the fastest way. You can do better than that. You can do faster than that. Okay. Here, so look at a special example. Yeah. Look at x to the 8th power. How about that? 8th power. Yeah. This 8, we know it is a power of 2, right? 2 cubed. 2 cubed. How about that? The number is special. We have special property. Why we do not take advantage of the special property? Right? We can take advantage of it. No question.
Is this like where you can reduce the number of multiplications, since like 8 is a multiple of 2, you can like do, instead of like repeated multiplications, you can do multiple square roots, or like So you can split up into
Right.
x squared, squared.
Yeah, yeah. Yes, you got a point. Yeah, yeah, you got. So go back, look at the title, repeated squaring, right? That's what we are going to do. Yeah, because power of 2, we can take advantage of it. Power of 2, right? Yeah, because look at the smart way to do it. Smart way. All right, yeah. Let's do it. Yeah. First, from x to x squared, one multiplication, right? Yep. X times x, one multiplication. All right. Next time, when you move to the next one, you can go faster. All right. How about, because you already have the x squared value, how about you multiply x squared by itself, just the one multiplication, you can go to x to the 4th. How about that? Another multiplication. Another multiplication, you can go from x squared to x 4th. You only add 1. You jump faster. X to the 4th. X to the 8th. This time, you already have x to the 4th. How about you just take another multiplication with x with itself, squaring. Here, that's the squaring. We keep doing squaring operation. We jump to x to the 8th. Another one multiplication, you can see, adding these 3 multiplications together, we only need 3 multiplications. We can find x to the 8th. Instead of Horner's rule, we need 8. From Horner's rule 8, we reduce it to 3. How fast it is. Think about that. Repeated squaring, how fast it is. Repeat squaring. Okay? All right. Let me ask you another similar question. X to the 1024. If we want to calculate this monomial, tell me the minimum number of multiplications we need. Minimum number of multiplications you need by repeated squaring. It's a power of 2. I think you know it. 10, great, yeah. Yeah. So here we want to compare the difference. All right. By Horner's rule, for this high degree polynomial, you need 1024. By repeated squaring, we only need 10. Look at the reduction, how big it is. Look at the reduction, how big it is. 1000 to 10. 1024 to 10. Is that huge? That's huge. Yeah, that's huge. Okay? Yeah. Yeah. So Horner's rule, we know it's smart, but not necessarily always smart, right? For general case, yeah, because general case, we don't have the pattern for the coefficients. So we cannot take advantage of any special properties. But for the special cases like that, we have the patterns, right? We can take advantage of it. How about that? Okay? All right, yeah. Next, let me give you another example. So here you can see, for this class, you really need to open your mind so for your thinking. You know, try very hard to explore all the possible ways to solve the problem. So here, let me give you another interesting example, and to see if you can solve it or not. This time, I give you this polynomial. All right. My question, because here I give you special numbers. There is some special pattern you can take advantage of it. Definitely you can apply Horner's rule. If you apply Horner's rule, you will get 4 multiplications. Based on our previous experience, can we take advantage of the pattern of the coefficients so we can apply some special property, take advantage of the special property, and do it faster? How about that? Do it faster. Yeah. Think about it. Yeah. Horner's rule. Yeah. Yeah. We assume Horner's rule, right? Answer is 4. Okay? The Horner's rule, the answer is 4. So that's our bottom line. Yeah. That's the worst we can do. We want to do faster than that. Yeah. That's the worst we can do. Okay? Yeah? So you should get numbers smaller than 4. Then it's accepted. Yeah. Worth the effort. Yeah. Otherwise, we just take the Horner's rule. Think about that. Anything special in this polynomial? Anything special? Any pattern you can explore. Yeah. Here, let me give you an important keyword. If you have that experience, you will get there quickly. Pascal triangle. Anyone knows Pascal triangle? Pascal triangle. That's the keyword. Okay. All right. Triangle. That famous triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. This 1, 4, 6, 4, 1. Related to our coefficients. Pascal triangle, these coefficients, what's the relationship? How do we take advantage of it? Take advantage of it. Special coefficients. You should take advantage of it. What's the meaning of that? Do you know the meaning of Pascal triangle? So here the knowledge, if you have the background, that knowledge, although you can do web search, but you need to study a little bit. Okay? Yeah. So here, let me tell you the meaning. Yeah. That one, the top one, corresponds to a plus b 0th power. The second line, the coefficients correspond to a plus b to first power. The third line, a plus b square. Okay? Then next line, a plus b cubed. Then this line corresponds to a plus b to the 4th. If you do the expansion, a plus b to the 4th, do expansion, multiply out, you get this, the coefficients, 1, 4, 6, 4, 1, based on Pascal triangle. All right. So from there, yeah, does it help? From there, a plus b, x plus 1 to the fourth. How about that? Our p of x equals x plus 1 to the fourth. X plus 1 to the fourth. How special it is. X plus 1 to the fourth. How special it is. 4 power of 2, right? Square. Repeated squaring. Can you do repeated squaring? Repeated squaring. Do repeated squaring. All right? Repeated squaring. First multiplication. Because we do not count addition. X plus 1, we do not count. All right? Think about that. We do not count addition. Because it's so cheap. We don't count it. Okay? All right. X plus 1 times x plus 1. This is the first multiplication. Okay? The second, x plus 1, yeah, here. So the second, x plus 1 square times x plus 1 square itself equals x plus 1 to the fourth. So that's the second multiplication. How about that? Total 2. You see, this polynomial, you need 2 multiplications by repeated squaring. Yeah. By repeated squaring, for first view, it may not be that obvious. How can you apply repeat squaring here? Because you identify it as x plus 1 to the fourth by Pascal triangle. Pascal triangle. So you identify it. You find the relationship. You just take advantage of it. Take advantage of it. You get answer. From 4 to 2. That's the answer. Try to use this simple example to get what we are doing in this class. That's the so-called smart way to solve the problem. Okay? Yeah. I do not give you very complicated questions. This is a simple question, right? But you can see, based by the knowledge we just learned, we can already do things like this. How good it is. How powerful is the knowledge? Think about how powerful is the knowledge. Without knowledge, you cannot do things like this. So that's the knowledge we want to learn in this class. Yeah. So many things like this. All right? Yeah. Okay, the break time. Yeah. So come back